Let's get started. Okay, last time we completed the study of alcohols. Okay, study of alcohols. Again, one of the most important topic for alcohols are these reactions. Okay, one reaction is the dehydration of alcohols, meaning removing a water molecules from an alcohol structure. Okay, water molecule is removed as H and OH. That's why we also call this reaction elimination reaction. You're eliminating an H and what? And an OH. Of course, OH is from the alcohol. The hydrogen is from the carbon what? Next to the OH carbon. Okay, that's why you end up with a double bond between these two carbons. Okay, between this carbon, you get an alkene from the elimination reaction. Okay, another reaction is called oxidation. We're removing hydrogens from the structure of an alcohol. Those two hydrogens are from the O and the C. Again, you can see those two atoms are next to each other, are adjacent carbons, adjacent atoms. The O and the C. You're removing the hydrogens from these two atoms. And then you create a CO double bond. Okay, a CO double bond. Depending on which type of alcohol you start with, your final product on the CO double bond carbon could either have one hydrogen or no hydrogen at all. So basically, if you have two hydrogens before, you will end up with one hydrogen on this carbon. If you had one hydrogen before, then you end up with what? No hydrogen on this carbon. Okay, they're both CO double bond compounds, but they're different types we're going to study in chapter 4. Okay, this one with the hydrogen, we call it an aldehyde. This one with the carbon with no hydrogen, we call it a ketone. Okay, there are different types of compounds we'll study in chapter 4. So these are, again, the reactions of alcohols. We'll have time today and also Wednesday to practice, and your quiz will be on chapter 3, okay, on a lot of these reactions. Okay, today, starting today, we're going to learn another type of organic compounds with the functional group OH. What's the name of functional group, guys? The OH group, the functional group. Hydroxy group. Okay, hydroxyl group. Now, if the OH is attached to an aromatic carbon, okay, or benzene ring, okay, for most of this, this class, we call the resulting compound a phenol. Okay, a phenol. And if you want to represent a general formula of phenol, you can use the AROH. People will know this OH is attached to what? Aromatic carbon. Okay, instead of using R, we use AR. AR stands for aromatic carbon and aromatic ring. Okay, again, we call it this type of group a phenol. And today, okay, we will use a couple of reactions showing you why they're different, why alcohol is different type of compound than phenol. Okay, we'll show a couple of reactions. But before that, I have some history of phenol for you guys to read. The discovery of phenol, the simplest phenol, the benzene ring with an OH, is actually one of the greatest discovery in the history of medicine. Okay, phenol, the use of phenol, the starting using of phenol saved a lot of lives in the history of medicine. Okay, before that, you can see that the post-operative sepsis infections accounted for approximately 50% of patient death after major surgery. Okay, because of infections. And in 1867, okay, a doctor called Joseph Lister, he started to use the solution of phenol to spray the operation bed, the ward, and the apparatus, and even the clothes of the doctors. Spray on those, and he found out the death rate decreased. Okay, decreased. And this is the picture showing. You can see an operation in the 1870s. Doctor they're dressing with their regular clothes, everyday clothes for operations. But you can see that this doctor or nurse is holding a spraying device. And they started to use the solution of phenol as an antiseptic reagent. Okay, and later on, because phenol is very irritant to the skin, and people replace the phenol with another reagent called boric acid. This one, okay, and also successfully saved lives. And there's a link for you to read about the use of phenol. Okay, nowadays we're still using phenol products in the hospital. Not phenol directly, but some phenol products. We will show that in a few minutes. Okay, this is one of the greatest discovery in the history of medicine. Here is the structure of phenol. Okay, again, the simplest phenol is just OH attached to a benzene ring. Naturally, phenol is a crystalline solid, like this. Okay, like this, crystalline solid. And normally, if you open a jar, a bottle of phenol, most likely it will give a very slight pink color. Okay, the reason is phenol is very easily oxidized by oxygen in the air. Okay, that's inevitable. Okay, no matter its storage, transit. So when you have a bottle of phenol in the lab, you will see the solid contains a very light and pretty pink color. Okay, the reason is phenol is oxidized during storage, during transit. Okay, and also we use that property of phenol later on in our daily applications. Okay, we'll mention both. Okay, so far we mentioned two properties. One's what phenol is used for what? For antisepsis. But phenol is irritant to the skin, very irritant, and also smells very bad. And number two is phenol is very easily oxidized. We actually take advantage of both properties when we apply phenol products in our daily lives. Now, before that, okay, take a look very quickly. Okay, the naming of phenols or the derivatives of phenols. Okay, we don't go over much lengthy in today's class because you guys have studied the naming of phenols in what? Chapter 2. You guys remember that? This is the pair name what? Phenol, right? So when you see an OH bond to the benzene ring, the name of this compound is named after what? Phenol. And you know this carbon will be what? Number 1 carbon. So when you name this compound with the derivatives like a bromo on this, all you need is name what? Name the bromo and what's the location of the bromo. So here you can call it what? 4-bromophenol or P-bromophenol. P stands for what? 1,4. Okay, 1,4. So you can either call it 4-bromophenol or P-bromophenol. There are two groups, so you can use O, M, and P. But again, it's not benzene, it's phenol. Okay, it's phenol. And the same, if you have multiple groups, you can just follow the rules we have studied before and name those compounds. Okay, take a couple minutes, take a look at number 3 and number 4. Do you understand the name? Or easy you can name these compounds? And number 3 and number 4, is that easy to name those? Or do they names make sense to you?
Number 3 is a little bit confusing. I think the
Which part?
Oh, not 3. I mean 1, 2, 3, 5. 5. That one because
I'm asking you 3 and 4. Number 3 and number 4 was the name. I just ask you first. Do those names make sense to you?
Yeah.
Perfect, makes sense. Okay, number 5, Amanda. Since you were asking, can you try name it? Confusing is fine. Just you try it first.
2.
What's the name of this group?
Methyl.
1 carbon?
Oh, methyl.
Methyl
So
group. What's the name of this group?
1, 2, 3, 4.
4.
Ethyl.
Ethyl.
And then
Phenol, right? And we put which one first? Ethyl first, because ethyl start with what? E. So 4-ethyl, 2-methyl phenol. Is that easy?
Yeah.
You did it, right? But again, so by now, I hope you guys see these group, you can know it right away. You don't have to think, because think about how many compounds you have named so far.
Yeah.
If you have done it, practice everything. So you don't have to think what the name of this group. You know they're ethyl and methyl. Okay. In your practice, like I told you, you guys won't see only a lot of complicated groups, especially in your test. All I need is you know what? Know the rules. How do we name these compounds? I won't test you like a really complicated groups, but these basic ones, you should know them very well by now. Okay, 4-ethyl, because ethyl start with E, 2-methyl phenol. Great. Okay, this one, Christine. 2,5-dibromophenol. Do you guys agree?
Yes.
Very good. Okay, see, beautiful. And again, bromo and phenol, there's no space, just one word. Okay, 2,5-dibromophenol. Perfect. Okay, there's a dash between number and letters. Okay. Perfect, good. That's for naming. Again, you guys, we have done this many times in our previous chapters. Okay, now these two reactions are the most important reactions of phenol for this class, and also show you why in phenols, these OH is different than the OH in alcohol. Okay. Phenols, the OH, the reason they're different, and also the reason why they're irritant to our skin, is because the OH, a phenol, is acidic. Okay, it's acidic. What does it mean, acidic? Okay, a definition of acid. Okay, a definition of acid is a compound when dissolved in water will give a species called hydrogen plus ion. Okay, I'll put it on board. Okay, hydrogen plus ion. Okay, this is the species. If a compound, when dissolved in water, releases this guy, we call that compound an acid. Okay, we call that compound an acid. Hydrogen plus ion. Okay, hydrogen plus. A little background. Hydrogen atom. Okay, hydrogen atom has one proton and one electron. Okay, hydrogen atom has one proton and one electron. Hydrogen plus, meaning the electron is what? Is gone. So what's left? A proton. That's why we call this hydrogen plus ion. Most of us call it a proton. Does it make sense, guys? You can call it hydrogen plus ion. No one call it wrong, but we call it proton more often. So what does it mean? What it means, if a compound, when dissolved in water, releases proton, a proton. Why we call it proton? Again, this is hydrogen. Hydrogen loses one electron, becomes a proton, because that's all it has left for hydrogen. Then we call the species what? An acid. When this proton released by acid is in water, this proton, because it's highly charged, it won't stay put by itself. It always grabs a water. Okay, again, it is in water. We have a lot of water nearby. Because this is too highly charged plus, it always grabs the water, or taken by a water to be more accurate. Taken by a water to give you H3O plus. You guys understand what's happening here? Water is what? H2O. Takes a hydrogen plus, give you what? H3O plus. What is H3O plus? We call it hydronium ion. What is it? It is a proton. It is how proton exists in water in reality. Does it make sense, guys? This is a proton. These two are the same thing. But this shows how proton exists in water. Does it make sense? Good. If you understand this, take a look at this react. What happened? Phenol. The H becomes what? H plus taken by what?
Water.
Water becomes what? H3O plus. Do you guys see that? Now when the H comes off as H plus, O becomes what?
Negative.
O negative. Do you guys see that? This is the reaction showing phenol is an acid. You guys know what happened, right? H is what? H plus. Okay, the bond, OH bond breaks. H as H plus, taken by water to become what? H3O plus. What is H3O plus? It's this guy. It's just water takes it. And then the O becomes what? O minus.
So these are both ions, right?
Correct. Okay, they're both ions. Charged means they have a charge on them. Okay, they're both ions. This reaction shows phenol is an acid. Does it make sense? What is an acid? When something dissolves in water, releases what? Proton. Again, this is a proton, but it's taken by water. Okay. In reality, all protons are taken by water. They won't exist by themselves. Okay. Good? Second. Because phenol is an acid, then it can react with a base, such as sodium hydroxide. Okay, or sometimes potassium hydroxide. These are two common inorganic bases. Now, how do we figure out the product, and how do we figure out the reaction? Okay, I'll put on the board, helping you to. Okay, this is phenol. This is the base. Okay, again, you can put the base as plus, or you can put it on top of the arrow. Either way. Okay, either way. Now, because it's an acid, again, when phenol is an acid reacting with the base, when this one is an acid, we know the hydrogen will be released as what?
H plus.
Guys, as what?
H plus.
H plus. Okay, so the best way, guys, for you, you can use a pencil to mark the hydrogen is actually hydrogen plus. The O is what?
Negative.
O negative, just mark it. Okay, even though they're not breaking yet in water, but you can mark it. Now in base, what is sodium hydroxide? Sodium hydroxide is basically sodium plus and OH
Negative.
negative. Okay, they have a lot of sodium plus and OH negative in sodium hydroxide. This is basically what a sodium hydroxide is. Sodium ion and hydroxide ion. So what happened is between these two, the acid and the base reacting together is the hydrogen plus and the OH negative react to give what?
Salt and water.
Water. Do you guys see that? H plus and OH negative give you what?
H2O.
H2O. Okay, that's first. H2O is the product between these two guys. That's the real reaction. And then whatever left behind is what? The O negative from phenol. Is that right? And what? Na positive from what? From sodium hydroxide. We call this one a salt. Okay, a salt. Does it make sense? Can the video show this part of the board?
Not the whole thing.
Not all the way. Okay, I'll put it on here. Okay, so the products are. Okay, I'll put it like this. Water. Again, water is from what? H plus and what? OH negative. And then the other product are basically what is remaining. Okay, they're not reacting. The reacting is the H and OH. O minus and what?
And
Na plus. Okay, this is an acid and base reaction. Does it make sense, both reaction? Okay, the top one shows it's an acid. The bottom one shows acid and base reaction. Okay. And you will see those reactions in your quizzes and tests as well. Now, you know after you copy, your eyes are on where? On where? On the OH. Is that right? What is the O? O negative. What is the H? Positive. The same here, right? What is the O? Negative. What is H? Positive. Positive just taken by what? By water. Okay, don't forget the charge. Okay, look for the charge. Okay, and you don't care whatever is on the rings, you just copy. And then your eyes are where? On the OH. Okay, that's how we work on these reactions. Right? And we never saw these on the alcohol. Okay, the reason is because of the O is attached to the aromatic ring. Okay? Okay, and because of this acidity, because phenols are acid, okay, use phenol directly. Okay, use phenol directly as a disinfectant is being very irritant to the skin, especially if you need to spray on the wound. Okay, later on, people developed some other phenol derivatives that has less irritancy but maintain the disinfectant efficiency for these compounds. For example, the one we use nowadays, Lysol, is a combination of these two. Hold on, which one? Of these two. Okay, of these two ingredients below. Okay, you can see this one also, such as the 4-hexyl, like a resorcinol, is an ingredient in many mouthwash and throat mouthwash regions. Okay, those two are the ingredients of Lysol. Okay, what's in common of these compounds? You can see that they're all what? They're all phenols. Is that right? They're just not using the phenol directly. They use the derivatives. Maybe they're even more efficient in killing bacteria and microorganisms, okay, but less irritant. Okay, much less irritant. That's why when you go to hospital, the floor they always have a odor. Is most likely the odor of these phenols. Okay, and also the discovery of the doctor who discovered the use of phenol, Joseph Lister, one of the brain of the mouthwash, is named after him, Listerine. You guys know that, right? Yeah. One of the mouthwash brain. Listerine is named after Dr. Joseph Lister. Okay, so that's how we use phenols, one as disinfectant. Okay. Another use of phenol is as antioxidant. Okay, antioxidant. Antioxidant use of phenol are mainly in commercial products and food. Okay, and in foods. For example, these two are FDA approved additives, all kinds of foods. Okay, for the foods. Antioxidant doesn't mean those compounds are not oxidized. Remember, we see phenol are what? Very easily oxidized. So why we add those? We add those so that when oxidation happens, they happen on what? On the phenol first. So they're actually sacrifices. To what? To prolong the shelf time of food. Does it make sense, guys? They're added as sacrifice. To what? To take oxygen away. So when oxygen happens on what? On this guy first. So your food can remain crispy longer, like your cereal, for example. Does it make sense? Okay. Phenols are very commonly used as antioxidants. They're not antioxidant. They're just what? Sacrifice in different products. Okay, again, these two structures, you can see that they are FDA approved additives in food. Okay, not only as additives, okay, our nature, our body has phenol as antioxidant too. I don't know, have you guys read articles, stories? Vitamin E is a very good antioxidant. We have those, and we take those. And this is the structure of vitamin E. It has a what? Has a phenol. Okay, it's a natural antioxidant. Okay, vitamin E. And besides that, if you guys drink tea, okay, tea is a very good source of a lot of polyphenols in their components. Okay, these are the structure or the chemistry of tea and milk. Okay, they both contain phenols. I'm sorry, the chemistry of tea. Okay, this is the effect of milk on phenols. Okay, when you add milk to phenols, and what happens? Sometimes the product can be taken out if you add milk. Okay, you can read if you're interested. Tea is a very good source of natural phenols. Again, as antioxidants. They're good for us. Okay, our environment is a reductive environment. So we want antioxidants to clear the oxidation reactions out of your cell resistance. Okay, we need antioxidants to get rid of those oxidizing agents that are damaging to our cells and biomolecules. Okay, if you're interested, you can read more on that. All right, that is all for phenol. You don't have to know the physical property. You don't have to know, just know some uses. Okay, because like I said, this is one of the greatest discoveries in the history of medicine, is phenol. And also those two reactions. Why phenol is an acid, and how does phenol react with a base? Okay, a base. Any questions, guys? No? All right, next. Let's take a look very briefly. Another type of oxygen-containing compound called ether. Now, ether, unlike phenol or alcohol, does not contain any OH group. Instead, on the oxygen of ether, there are two carbons attached to it. Okay, we know oxygen has how many bonds? Two bonds. In ether, both bonds are bonded with what? With carbons. There's no hydrogen anymore on this compound. So the functional group of ether is what? It's COC. Okay, an oxygen bonded with two carbons. And those two carbons can either be aliphatic or aromatic carbon. Doesn't matter. They're all ethers. So the general formula of ether can be ROR or ROAR. Doesn't matter. As long as there's a carbon attached to oxygen, two carbons attached to oxygen, regardless of the types of carbon, those compounds are classified as ethers. Okay, these are the bottom three. I'll give you a few examples of. You can see they're all ethers. They can be simple carbons. They can be carbon and cyclohexane, cycloalkane carbon. They can be carbon and what? And aromatic carbon. These are all ethers. Their function group is what? COC. Okay, they're all ethers. Okay, those first is the structure. What are ethers? Ethers is an oxygen attached to two carbons. The naming of ether, okay, naming of ether can be two different ways. Okay, one way, simpler, but is not a universal, is to use the common name of ether. Okay, not our systematic name, common name. But again, it's easy, but not universal. That means you probably cannot use common name on all ethers. Some ethers you can use that. And for you, if you name those ether, either way, if you can figure out the common name, you can use common name too. It counts as correct. Okay, so here, this picture shows you how do we name an ether using common names. Common names of ether is simply you list the two groups attached to the oxygen, alphabetic order, and followed by the word ether. Remember, what is ether? What is ether? COC or what? RO what? R. That means what? There are two groups on what? On the oxygen. So if you name a common name of ether, all you need is name those two groups and list those names in alphabetic order, and then followed by the word what? Ether. Does it make sense, guys? Okay, take a look at the names. Do they make sense to you? Or can you recognize the group quickly by now?
So the last two, it could be either dimethyl or just methyl?
Correct. Correct. If you call it methyl ether, means we know those two groups are the same. They're both methyl. Correct. We call them methyl ether too. Again, those are common names. Common name means people are using those names. They accept the name for a long time. Okay, that's why there's no rules or much. We use those names. Okay, diethyl ether, the same. Correct. But you can use di if you don't want to confuse with the rules we learn every day. So forget about the one in the parentheses. Just call it dimethyl ether or diethyl ether. Okay, even though it's a common name, but still kind of like follow the rules. Okay, 2 ether, 2 methyl group, 2 methyl group. Does everyone make sense, everyone? Okay, this next group we call what? Phenol group, right? The group from benzene ring is called what? Phenol group. And this is the isopropyl group. 3 carbons, it's propyl. Why isopropyl? Because attached to what? To the middle carbon. You guys see that? 1, 2, 3 attached to the middle carbon. So it is isopropyl phenol ether. Okay. Isopropyl start with I, phenol start with P. So isopropyl phenol ether.
So for phenol, there should be an H with the O, right?
Which one?
Second one.
Yeah?
So there should be an H with the O, OH.
Which,
right?
where? Here?
Yes.
What meaning OH? This is a carbon.
Yes. So for phenol, the group attached to benzene should be OH, correct?
Attached to benzene should be OH.
No, like when OH is attached to a benzene, that's when we call it
Phenol. But
yes.
it's OH. This is not OH. There's no
oh,
H.
it's a phenyl. Sorry.
So that's an ether because this oxygen has no H on it.
Yes, C6H6, H5, correct?
Correct. This is C6H5
Yeah.
because there wasn't hydrogen here, not here.
Yeah,
Nothing
yeah,
nothing to do with the oxygen. There was an H here on the benzene, but if you want to group, the H is gone. That's why the carbon can attach to the O.
Yeah.
Yes.
I got confused. So
Yes.
thank you.
I see what you mean. Yes.
Yeah.
All right. That's common name. Okay. And of course, the more universal way, okay, you won't make a mistake, is the systematic name, the IUPAC name. Okay, IUPAC name. Ethers are named as derivative of alkanes. Okay, derivatives of alkanes. So when you name an ether, the name will end up with an alkane. The name is an alkane. So how do we name the O? Remember, ether has what? Has oxygen. So how do we name the O? When you have an ether, you choose the longer group as the longest chain for the name of the alkane. Then the smaller group plus the O becomes a group of the alkane. Does it make sense, guys? So how do we name the smaller group with the O? You drop the YL of the group, replace it with OXO. I'm sorry, OXY. Oxy. Okay, well, oxy stands for what? Oxy. Okay, for example, this is what group? Methyl group. You replace the YL of the methyl with what? Oxy. So the whole thing is called methoxy group. Does it make sense, guys? And the methoxy group is on what chain? Butane. Which carbon? 1. So 1 methoxy butane. You guys see that? Okay, the longer group, the bigger one is the chain, is the alkane. We said ethers are named as alkanes. And the smaller one plus the O becomes a what? Becomes a group. Okay, becomes a group. The bottom one. This part is the bigger one. So the longest chain is what? 3. And there's a methyl on number 3. That's fine. Okay, 2 methyl. But there's a what? Smaller group ethyl with the O. Ethyl becomes ethoxy, right? Ethoxy or ethoxy. And where is the O attached to? Number 1 carbon. So 1 ethoxy, 2 methyl propane. You guys see that? Okay, take a look. I can explain if it doesn't make sense. First, you have to know the No, it doesn't matter. Not necessarily. No. In here is 1 because the oxygen attached to this carbon, you have to name this carbon number 1. Then that's 2. Okay, that's always 2, but this could be 1 or 3. Of course, you do that number 1, yes.
Okay.
But not no, it's not necessarily has to. No.
Okay.
Yeah, you just find the longest chain. You figure out then where's the O. You look at the O. In these 2 cases, it happened to be number 1 carbon, but not always 1. Does it make sense, guys? Okay, those are all alkenes. Your name will end up with an alkene. The only thing is you may make a group. All right? So don't look at the name I gave on the board, and you just try to name it by yourself. Again, don't look at the name. Draw the structures, and then on your note, and then look at your note and name it. Then raise your head and look at the answer. Let me know if it doesn't make sense. Even if you check the key. Yes.
This one. So we have to start like okay, so this is pentane.
Correct. And that's number 1 because there's a group on it. That's the chain, pentane, correct. But when you number it, because this is group, right? Once you find the chain, everything else is a group. So the group should have the what? Lowest number possible. Then you should number this carbon as number 1 because that's where the group is attached to.
Oh, so
Not that number 1. 1, 2, 3, 4, 5. You got it.
And then this is so if you separate it, then that would be 1.
I'm sorry?
If you so like that's pentane, and then you would start here because that's the other group.
Yes.
And then you would why would that one be 1? Why is O 1?
O1 is this carbon is 1.
Okay.
I said you number this carbon 1. That's number 1 carbon.
Oh.
Has nothing to do with numbering here. As the numbering is on the chain, on the longest chain.
Okay.
The 1 indicates where this group is attached to. Here is the where attached to.
Oh, okay.
That's the number 1 carbon, not 5.
Okay.
Does it make sense?
Yes. Thank you.
All make sense?
So I have a question, it's probably
Yes.
a stupid question, but we see that O is attached to on both sides. So do we pick the smaller group when we are naming it?
When for ether?
Yes.
Yes, always, like I said, once you pick this one is the longest chain,
Yeah.
then the other side will be the group.
Yeah.
But when you name the group, you have to include that O as well. So once you pick this part is the longest chain here,
Thank
this
you.
part longest chain, then everything else here is what? Is the group.
Yeah.
And the group is propyl changed to what? Propoxy.
Propoxy.
And where is the O attached to?
Pentane.
This carbon. Is that right? So we now number this carbon what?
1.
1. Okay, again, this is the chain. When you put the longest chain, you can draw a circle or use pencil, whatever. The chain is 1, 2, 3, 4, 5.
Thank you.
Make sense? Okay, the same here. Like Kristen was asking, does the O always has to be number 1 carbon? No, this is showing you an example, right? Now this O is attached to what? This carbon. The longest chain should be 1, 2, 3, 4, what? 5. So this is where the O attached to. That's what it's 2-carboxy pentane. See that? Again, guys, when you name those, I know you're done. We practice, you know the key. Cover this. Ask yourself, why 3 times? Like until you can explain to yourself. Or you can even cover the structure, erase the structure based on the name. Can you draw the structure back and forth, back and forth? Okay, those are practice. We have 4 examples here, including the ones previous page. Okay, you practice 5 more. I think you should be very good in naming ethers. Okay, please practice. Okay? Next. The physical property of ether is very similar to alkane, especially the boiling points. Okay, the ether, because of there's no hydrogen on the oxygen, so there's no way you can have hydrogen bonding, unlike the alcohols. And because of that, ethers, the molecules between the ether molecules, the interactions are very weak. So the boiling point of ether is very low, very similar to hydrocarbons. Okay, very similar to hydrocarbons. Okay, ethers are very volatile too. Okay, very volatile too. But because ether does have oxygen, so for some very small extent, the oxygen can interact with the hydrogen of water through hydrogen bonding. Okay, this is O, that's H. See that? Of water. And because of that, because of this O, small ether molecules have a very small extent of water solubility. Okay, not much, still not much, but will dissolve in water in a very small extent. Okay, very low water solubility. But better than hydrocarbons. Okay, slightly better than hydrocarbons. Most importantly, ethers is another greatest discovery in the history of medicine. Okay, if you want to name 2 greatest discovery in the history of medicine so far, phenols and ethers are the greatest ones. In what? As anesthetic agents. As a matter of fact, diethyl ether. Do you guys remember what is diethyl ether? We've seen that very first picture of ether. What is diethyl ether? 2 ethyl groups on what? On oxygen. Is that right? That is the first anesthetic ever used in surgical operation. Diethyl ether is a liquid. So in early ages, I don't know, you guys can take library of medical history. You should put something on the patient's mouth and start adding drops to the nose, to the like a gauze, so that the patient breathe in ether. And the amount of the time it lasts is very short, so you're going to keep adding that during the operation. But that's the first time we used anesthetic during an operation. But nowadays, of course, okay, nowadays, we no longer use diethyl ether, but the ones that we use nowadays, if you guys later on becomes a CRNA, okay, you will use these a lot. The one we used as gases to breathe things, anesthetic, are still ethers. You can see that. You guys see that? CO what? See, they're all ethers. The only difference is these are highly fluorinated. Okay, have a lot of fluorine in their structure. Okay, these are the ones commonly used nowadays. Okay, as anesthetic. Okay, and very quickly here, you don't need to know for the purpose of your test and quizzes for this topic. Ethers are not only they're flammable, okay, they're also very easily oxidized into a compound like this with 2 oxygen in the middle. We call peroxides. Okay, they're very explosive. Okay, that's why ether storage is very tricky in the lab. Okay, you have to make sure it does not burst in fire. Of course, they're flammable. Number 2 is you cannot store ethers for long. Okay, because long storage will generate more and more this peroxide. It will be very explosive. Okay, and that's the same reason you store gasoline in your garage. You cannot store for long. The same reason is the generation of peroxide. It's lower than ether, but there's a chance of generating these type of compound. Okay, that's very hazardous. Okay, and then ethers, we know there's ROR, but we do have a class of compounds called cyclic ethers, meaning the oxygen is part of the ring. Okay, oxygen is part of a ring. And you can see that they all have the same functional group of COC, if you take a look. Because oxygen is what? Is part of the ring. Is that right? And when you have part of ring, then you have what? COC. COC. These are all ethers. We call them cyclic ethers. Okay, we'll save the structure here. We'll see these types when we study chapter 7 on carbohydrates. Okay, carbohydrates. Okay, they have similar structures of cyclic with oxygen part of the ring. Right? And finally in this chapter, and again, you won't see those types of compound in your tests. But I do want to introduce you, since we're studying oxygen-containing compound. Okay, another type of compound which are common in nature or around us in our lives is if we replace the OH of an alcohol with a sulfur, okay, or replace the O of OH of an alcohol with a sulfur, so we get an SH. Okay, if you look at the periodic table, S and O, they're next to each other in the same group. Okay, in the same group. We get a new types of organic compound. We call those thiols. Okay, we call those thiols. The thiol, the word comes from the sulfur. Okay, the group is no longer called a hydroxyl group, called a sulfhydryl group. Okay, thiols are important groups of organic compounds. Again, they're around us. You just didn't realize. Okay, one property, a well-known property for thiols is they smell really, really, really bad. Okay, they smell one of the most unpleasant odor in organic kingdom, like a realm. Okay, and we utilize those. Okay, not only they're around us, we utilize those odors as well. It's not just all bad. Okay, for example, methanethiol. Okay, methanethiol, which means methyl group with a thiol group, is a byproduct for the metabolism of asparagus. I don't know if you guys eat asparagus. Sometimes people eat asparagus. They cannot metabolize the methanethiol, so they may have bad breath, or the pee smell really bad. You guys try next time. Some of you may cook the different genes, different people. Okay, people I know of, they all know they have the experience. You don't have to smell the pee on purpose. But next time if you have breakfast, if you pay a little attention, you'll find out it's very unique because style, the odor is very unique. Okay, depends on you. Okay, it's not all. Some people cannot metabolize it, but most people I know of, they will have the same experience. Okay, another one, ethanol, this guy, is added in natural gas on purpose, very tiny amount. You guys, when you turn on the gas stove without light like igniting it, you smell it, right? That's not the gas of the natural gas, odor of natural. That's the odor of this guy. Okay, natural gas has no odor. Natural gas is methane. It's odorless. You won't know it. What you smell is a tiny, tiny amount of this guy, because they smell so bad. Even the tiny amount will give a strong odor. And the last one is the smell of the compound responsible for smell of skunks. And besides those, some most unique odor in nature, like onion, broccoli, garlic, they're all because of SH. Okay, when you have a vegetable or food with a weird odor, most likely it's because of this guy, SH. Not all bad. Okay, thiols are very good, healthy. Onion, garlic, broccoli, they're very healthy food because of the thiol. Okay, they can serve as an antioxidant again. Okay, and this reaction, again, we don't talk about this whole in this chapter. We will see this reaction again in chapter 8 chapter 9 when we study proteins. Okay, proteins, because one of our amino acid does have a thiol group. Okay, it does have a thiol group. So we will see this reaction again in chapter 9. Okay, two thiols will make a bridge, like SNS, a disulfide linkage, which is very common in our proteins. Okay, we have a lot of that linkage in our whole body, in your hair, your skin. Okay, we have a lot of these bridges of proteins. All right, that is all for this chapter. Can you stop the recording? Do you guys any